So after adding and subtracting comes multiplying and dividing. So the first thing we're going to do is learn how to multiply radical expressions. It's the same as you would multiply polynomials. The same rules apply. So if we have root 2 times 3 times root 10 minus root 2, you are going to distribute the root 2 through the second bracket. So this is going to become root 2 times 3 root 10 minus root 2 times root 2. So distributing this through, it's root 2 times the first term, root 2 times the second term. You don't have to write this out if you don't want to. What I want to show you here is that you're left with root 2 times 3 times root 10. You are allowed to multiply radicals together as long as they have the same index. So we're going to do that. The 3 times root 2 times root 10 is root 20. Then here you've got root 2 times root 2, so that's going to be root 4. Now you always have to check with radicals whether you can simplify. So the highest perfect square that divides evenly into 20 is 4 with a factor of 5 remaining. And then the square root of 4 is 2. Keeping on going, you've got 3 times the square root of 4, which is 2, times the square root of 5 minus 2, gives us 6 times the square root of 5 minus 2. So you're going to distribute, you're going to simplify, and then you're going to keep simplifying. All right, next one. We've got the square root of x times the square root of 2x. So you're going to end up with the square root of 2x squared. Plus, again, you're going to distribute the square root through. You end up with the square root of 8x squared. Now you're going to simplify each radical. So 2 is prime, so it's going to go in the second bracket. The x squared is an even exponent, so it's a perfect square. I'm going to just keep going with that, guys. The square root of x squared is x. I'm left with square root of 2. For this one, I'm going to again separate it into 2 radicals. The square root of 8. 8 can factor into 4 and 2, and then the x squared is an even exponent again. So that one, the square root of 4x squared is 2x, and I'm look at that, left with a root 2. So now I have like radicals. I have x root 2's, and I'm adding 2x root 2's, so I have 3x root 2. And again, if it helps you to see it, you can see that they have a common factor of root 2, and then if you factored out the root 2, you'd be left with an x. If you factor out the root 2, you'd be left with a 2x, and maybe that helps you see that 3x times root 2. All right, going a step further, if you have binomials that are multiplying, it's still just a giant distribution. We've got 3 root 5 times root 5, which would give me 3 times root 25. Then you've got 3 root 5 times 4 root 2, which would be 12 root 10. Then you have negative root 2 times positive root 5 would give me negative root 10. And then I have negative 1 root 2 times 4 root 2. So you're going to do negative 1 times 4 is negative 4. And root 2 times root 2 is root 4. Then we're going to simplify. These front term and the last term ended up as perfect squares. So this is 3 times 5. Here you've got like terms in the middle. So 12 root 10's minus 1 root 10 is 11 root 10's. And then here you've got minus 4 times root 4 is a perfect square. So we're going to say times 2. So then we've got 15 minus 8, and you end up with 7 plus 11 root 10. All right, moving on to the next question. You could totally pause the video right now and give this one a go. There's nothing new that's going to come up in these next 3 examples, but let's get through them. So we've got 2 times 3, which is 6, and then root 3 times root 3 is root 9. You've got distributing through the second term, you've got 2 times negative 2 is negative 4. Root 3 times root 5 is root 15. Then here you've got negative 3 times positive 3 is negative 9. Root 5 times root 3 is root 15. And then lastly, negative 3 times negative 2 is positive 6. And root 5 times root 5 is root 25. Then we're going to simplify. This is going to be 6 times 3 Then you've got negative 4 root 15s and negative 9 root 15s. So you've got negative 13 root 15s. And then this would be plus 6 times 5. Now I'm going to collect like terms. I've got 18 plus 30. So I have 48 minus 13 root 15. Now, when you're doing this work, I mean, if you wrote this in a different order, if you had negative 13 root 15s plus 48, commutative property addition, it's not wrong, but standard notation for anything with a radical is that the radical part of the expression comes second. So that's why you'll see me constantly writing them in this order. Okay, last example. Hopefully you recognize this guy from chapter 4. If you have a binomial squared, that means you have 2 plus root 6 times 2 plus root 6. Up to you if you remember the trick for expanding a binomial squared, feel free to do it, but I just like going the old school, just distribute. 2 times 2 is 4, 2 times root 6 is plus 2 root 6. I don't know if this screen is glitching for you guys, but it's glitching like crazy for me. Okay, and then you have the root 6 distributing. Root 6 times 2 is 2 root 6, and then root 6 times root 6 is root 36. And then again, we simplify. We've got 4, and then we have 2 root 6 plus 2 root 6 is 4 root 6. And then we've got the square root of 36, which is 6, which leaves us with 10 plus 4 root 6. All right, last example. Oh, look at that. It reminds you of factoring a difference of squares. They are complement binomials where they're the same, but with opposite signs. When you multiply this out, maybe you remember that your middle terms are going to go away. So we're going to distribute the root 5. We get root 5 times root 5 is root 25. Then we've got root 5 times positive root 3 is root 15. Then we've got negative root 3 times positive root 5 is, let's put positives on there, negative root 15. And then lastly, we've got negative 1 root 3 times positive 1 root 3. So we've got negative root 9. Then we're going to simplify. Square root of 25 is 5. Plus root 15 minus root 15 is 0. So then we have minus 3. And we get 2 as an answer. So that's going to be a really important concept coming up in the next video or two, depending on how long they take me. But if you multiply two complement radical binomials together, then what you're going to notice is that the radical goes away. You end up with this beautiful whole, not necessarily whole number, but integer answer.